All right, so here is a Gauss problem, Gauss's law, that states, consider the charge distribution below composed of two concentric spheres. The inner sphere of radius A is insulated and charged with non-constant charge density, rho r equals rho sub 0 A over r squared, while surrounding it is a neutral conducting spherical shell of A less than r less than B. So for question A states that to find the electric field for r less than A. All right, so how can we start this? Well, first thing we need to know is that this equation right here, that is the charge density. So charge density of rho r equals rho sub 0 A over r squared. Now it's going to be very important considering the fact that that itself represents the insulated charge sphere of radius A. All right, so how can we start this? Well, first thing we need to know is the equation that we have to use, and that's going to be the electric field equation. EdA equals Q enclosed over epsilon naught. Now, to find this, we can first take Q enclosed and see what it means. So Q enclosed, for this context, is going to be the integral from 0, that's the very, very center here of the volume of the circle, of the sphere, and all the way to r, which is what we're looking for. So that's going to be the integral from 0 to r of rho r. Now we're going to prime that times 4 pi r prime squared. 4 pi r prime squared dr squared. So what is this? Well, this is basically taking the charge density times the surface area of the sphere is what we're looking for. Now, you could be asking, well, aren't we looking for the volume of the sphere, not the surface area? Well, technically yes, but in this context, the 4 pi r squared, that's the infinitesimal surface that we're looking for. That's the charge that is being distributed within the insulated charge sphere, not exactly the volume. The volume implies, volume is going to be 4 pi r cubed. That's implying we're looking at everything within inside of here. Now, although that does seem correct, we're looking actually at the infinitesimal surface charge of the insulated sphere right here. Hence why we use this guy and not this guy. All right, so now we have Q enclosed set up. How can we, well, solve this? Well, first of all, you can recognize that rho r is this guy right here. So let's plug that in. It's going to be from integral from 0 to r of, let's make that a little thin, rho sub r of rho, whoops, yeah, that's the symbolic formula, of parentheses rho sub 0 of A over r squared times 4 pi r, whoops, 4 pi r prime squared times dr. I forgot to mention, let's remember to put the prime in the denominator of the r right there as well. Right, now the first thing we can do is we can recognize that there are some coefficients, some constants, that we could move in front of the integral, such as rho sub naught, a, 4 pi, because what we're doing is we're basically integrating r. R is our focus right here. Let's make that blue. R is our focus, and that's what we're derivating, not dr, but the denominator r prime and r prime squared. That is the focus that we're looking for. So let's just move all the constants in front. So that's going to be rho sub naught, a squared, and 4 pi to the integral of, now what we're left is 1 over rho prime squared times rho prime squared dr squared. Not dr squared, sorry, just dr. Right now we can see that we can cancel out these two rho prime squares. And now we're left with rho naught a squared 4 pi from 0 to rho, or 0 to radius r of 1 dr prime. Now what we can do from that is simply integrate. So that's going to be, again, the constants and r minus 0. Now that's just going to equal rho sub naught a squared 4 pi r. Okay, are we done here? No, we're not done here, but we now know Q enclosed. So this guy right here is going to be Q enclosed. That's what we're going to be plugging back in here. Now it's going to be EDA of Q enclosed, which is going to be rho naught a squared 4 pi r over epsilon naught. Now, if you look at the Gaussian symmetry of dA right here, dA for a spherical is also going to be 4 pi r squared, just like the one that we used last time. So let's substitute that in. It's going to be E 4 pi r squared equals rho naught a squared 4 pi r over epsilon naught. Now we're trying to look at the electric field here, so we're going to isolate the surface area of the sphere of dA, and that's going to equal electric field equaling rho sub naught a squared 4 pi r over epsilon naught times 4 pi r squared. Let's move that guy a little bit down here. Right now we can start canceling out. It's going to be, we're going to cancel 4 pi's, the r and the r squared, and we're left with the electric field equaling rho sub naught a squared over epsilon naught r. So that's going to be the very first electric field for question A. Now remember, it's asking for r being less than a. The radius has to be less than a. So it's going to be from here to an arbitrary point here, for example. Now the reason why we can't use a is because, well, it states right here that r literally is less than a. So there's going to be a little bit of space here to take into account if we do a as well, which we're not going to do that because it's going to be a futile step and we would just take the bounds of 0 to r, which is going to be easier. But from what I just said, now we move on to B, which is to find the electric field from r greater than b. Now this one is a little different, and you will have to, and you'll have to understand why r is greater than b and how we're going to set this whole thing up. So the first thing we have to know is that the area, the region here, all the way down, all the way in here, between the radius of A and B is a neutral conducting spherical shell. So a neutral conducting spherical shell basically means that there is no charge within the space confined, because neutral conducting spherical is a spherical object with no internal charge that allows electrons to move freely. Now, when an electron moves freely, considering it's a neutral space, electrons are evenly distributed between the space. So now what we can do here is to assume that if R is an arbitrary point outside of the spherical charge, then considering that the electric charge in this region is 0, all we need to do basically is to just find the charge from 0 to the A radius. That's it. That's just it. Because considering the fact that everywhere else here, E field equals 0. So all we need to do is to basically just take the charge of, well, the charge from 0 to, well, radius A right here. So we can start off by knowing that Q enclosed, electric field is equals Q enclosed over epsilon naught. And we're going to use epsilon naught, or Q enclosed, sorry, which is going to equal 0 to, like I said, A of rho r prime times 4 pi r prime squared, 4 pi r prime squared times dr prime. Now let's substitute this. So this guy right here is going to be rho sub naught A over r squared times 4 pi r prime squared times dr prime. All right, now that can turn into moving the constants in front again. So that's going to be rho sub naught 4 pi A squared, and yeah, that's it. Move that in front of the integral from the bounds of 0 to A, and all we're left is 1 over r prime squared times r prime squared times dr prime. Now let's cancel those out, and we're going to get, again, the coefficients out in front, rho naught 4 pi A squared from the integral bounds of 0 to A of 1 dr prime. Right now we know that the integral of 1, based on the values given here, is going to be r. It is with respect to r, so it's going to turn into r minus, respect to A, I'm sorry, so it's going to be A minus 0. So this then turns into rho naught 4 pi A squared A. And since A squared and A, we can put that together and get rho naught 4 pi A cubed equals Q enclosed. Or now that we have Q enclosed of 4 pi A squared, we got to plug this back in to the electric field equation, or the Gauss equation, sorry. Which is going to be EDA equals pi A cubed epsilon naught, and remember that dA here again is the surface area of the sphere, 4 pi r squared. And now all we have to do is isolate E. So we first, obviously, set it equal to both sides, or divide 4 pi r squared by both sides. And now we're going to get the cancellation out. of 4 pi. And now we're left with rho naught a cubed over epsilon naught r squared. So in conclusion, the electric field as radius is less than a is going to be rho naught a squared over epsilon naught r, I believe, yes. And b is going to be rho naught a squared over epsilon naught r squared.